In the last lecture, we learned a couple of really important things, so let me go over that just a little bit. I just want to spend a little bit of time talking about the results from last time because we're going to build on those results this time. So first of all, we considered just this very simple chemical reaction. We're looking at the thermodynamics of chemical reactions. We saw that even that simple chemical reaction covers a lot of cases. All of the chemical reactions proper that have only one reactant and one product, also transfer processes between one place and another, and phase changes between one place and another. Then we saw that if we use a little bit of the machinery, the mathematical machinery that we developed earlier for thermodynamics, that we can derive a driving force, a change in Gibbs free energy, which is related to change in the entropy of the universe. And we saw that that driving force depends on the difference in chemical potentials between the reactant and product side. It's the chemical potential of the product side minus the chemical potential of the reactant side, and that's the net driving force. When these two guys are equal to each other, there is no net driving force, and we're at equilibrium. So when this is equal to 0, then we're at equilibrium. If the driving force is positive, that is, if the chemical potential of the products are bigger than those for the reactants, then that's unfavorable. Further reaction is unfavorable, and the reaction will actually go backwards. But if it's the other way around, if this quantity is negative, that is, the chemical potential of the products is smaller than the chemical potential of the reactants, then the reaction will go forwards. Yes, that's what all that was. All right. We also saw last time, the other thing we talked about was this equation of state for the chemical potential, and specifically how the chemical potential depends on the activity or concentration of chemical species. And we derived from statistical mechanics, from first principles, not quite from the ground up, but from this point on anyway, assuming that we believe that this partition function really is. Let me, since this Q gets used later, let me point out that this partition function is not the same as the reaction quotient that we come up later. They're both capital Q, but they're different quantities. Anyway, once we take this to be a given, then we can use the fact that the Helmholtz free energy is minus kBT times the logarithm of the partition function, and the fact that the derivative of the Helmholtz free energy is the chemical potential, after that just becomes algebra, to derive our equation of state for the chemical potential. And the real reason, the only reason really for doing that derivation is so that we could understand what role each of the terms in this equation of state is playing, and also where they come from, what effects, what physical properties they're accounting for. And we saw that this log term at the end, this log of activity term, is accounting for translational entropy changes in the chemical reaction, and it's universal, doesn't depend on the nature of the reactants or products. And the other term, this constant term, is accounting for everything else, all the molecular properties, rotations, vibrations, the nature of the solvent, the temperature and the pressure, the bonding, and everything. All that other stuff is buried inside this term. All right, this time we're going to apply those two ideas to the difference in chemical potential, that is, and then our expression for the equation of state for chemical potential. We're going to apply those things to deriving, well, what we're going to get to is this relationship down here, which should look familiar from freshman chemistry and probably from other classes as well, that the change in Gibbs free energy, the change in molar Gibbs free energy, that bar means this is a molar Gibbs free energy, for a chemical reaction is equal to some standard state change in Gibbs free energy plus RT times the logarithm of this reaction quotient. And again, that reaction quotient is not the same thing as the partition function up above. And we'll talk about that. We're going to derive it first for the simple case, and then we'll derive it for the more complicated case. So for the simple case, first of all, we already have this, that the rate of change of the Gibbs free energy with respect to mole numbers is equal to the difference in the chemical potentials between the two sides. Now we just plug in our expressions for the chemical potential equations of state for species A and the one for species B. And then it's just algebra. So we plug these two expressions in, and then we do a little bit of rearranging, and if we do, we get the following. We get that this difference in chemical potential between the product and reactant sides is equal to a standard state chemical potential, that comes from these terms, plus RT times the logarithm of the ratio of the activities for species B over species A. In other words, it's products over reactants, activity of products over activity of reactants. And that's in fact a simple case, a special case of a reaction quotient. And it's unfortunately given the same symbol as a partition function, Q, capital Q. Also, we saw earlier that for a single pure substance, the chemical potential is the molar Gibbs free energy. It's the Gibbs free energy per unit mole. And that means that we can just rename all these chemical potentials. I mean, there's no reason not to stick with chemical potentials here. In fact, or at least there's no logical reason. But for historical reasons, people have used Gibbs free energy instead. They use the symbol G. They basically just rename things. And I'm not sure what the history of that is, why that's so. But in all the textbooks and all the literature, you won't see people using chemical potential symbols. You'll see them using Gibbs free energy symbols, so we'll do the same thing. It really is just a renaming. Nothing has changed in going from here down to here, except that we're using different symbols. But all right, we'll do that to be consistent with the rest of the world. If we do that, then we just rename that, we rename that. This term doesn't change at all, and we get our familiar expression for the change in Gibbs free energy. This change in molar Gibbs free energy really is just the difference in chemical potentials between the product and reactant side. This standard state change in Gibbs free energy really is just the change in standard state chemical potentials between the two sides. And then this logarithmic term at the end really is, in this case, it's just these guys. It's RT times the logarithm of the ratio of the activities of products over reactants. All right. As before, because of where all these pieces or terms came from, this standard state term contains all the molecular properties, all the molecular information. It contains all the information about bonding changes that take place in the course of the chemical reaction. So if bonds are broken or formed, the energies involved with that are accounted for in this standard state Gibbs free energy. If the molecule changes its rotational properties, in other words, if the products rotate more or faster than the reactants did, those kinds of effects are also accounted for in this standard state delta G. Same for vibrations, same for changes in the masses of the molecules and so on. All those things are buried and hidden and packaged up neatly inside this one number, delta G0. And the other term, because it comes ultimately from these terms in our chemical potential expressions, accounts for changes in the translational microstates during the course of the chemical reaction. Or in other words, the changes in translational contributions to the entropy during the course of the chemical reaction, and nothing else. You'll notice that this Q is just a ratio of activities, and the rest of this doesn't have any molecular information in it. It's just an RT and a logarithm. And so there's no molecular information in this end. The only information in this whole term is about concentrations, not about molecular properties. And that's because all it's really accounting for is the fact that as the chemical reaction changes, the molecules either gain or lose the ability to move around in space, and that causes changes in the entropy, and this term is accounting for those changes. All right, that's for our simple case where our reaction is just A goes to B. We can redo everything without very much change from this point on with a more general case where we've got two reactants and two products and stoichiometric coefficients that aren't just all ones. So any stoichiometric coefficient, any set of products and reactants. And the derivation is almost the same. In this case, the change in the Gibbs free energy, that is the driving force, has four terms. Now it's got, well, it's got six terms really, but these first two terms go to zero. There's a term that depends on the change in temperature, a term that depends on the change in pressure, but there is no change in temperature, there is no change in pressure. These are all processes that take place in the presence of a temperature and a pressure bath, so dt is zero, dp is zero. And then four terms because there are four species, right, A, B, C, and D, involving the chemical potentials for each of the species and the mole number changes for each of the species. So there's four different possible ways in which the mole numbers can change. The mole numbers for A, for B, for C, and D can also all change, but they can't change independently of each other, right? If we look at this chemical reaction up here, every time I lose a molecule of A, I have to also lose B molecules of B, and I have to gain C molecules of C and D molecules of D, and that means that these changes in the mole numbers aren't all independent. They're all related to each other, in fact. And there's a way to express that relationship. We do it as follows. This is the sort of standard trick that you'll see in every Chem book. The number of moles, the change in the number of moles of species A is equal to a minus sign, because it's a reactant, times the stoichiometric coefficient for A, times a little squiggly change in quantity, and that's just really just a sort of a dummy variable that has a name. It's called the extent of reaction. And what that is, well, we're going to get rid of it at the end, so we don't really need to know much more about it. Suffice to say that mathematically, this allows us to get all the stoichiometric relationships between all the changes in a nice way. So the change in the number of moles of B is just the stoichiometric coefficient for B times this same extent of reaction. Same for C, except notice now a plus sign for the products rather than the reactants. So the stoichiometric coefficient for C times dC, and the same thing for D, and so on. If we plug those relationships now up into here for dG, then we get this relationship. Now this extent of reaction has factored out of all four terms, and we're left with only the stoichiometric coefficients times the chemical potentials for each of the species. Notice minus signs for the reactants, plus signs for the products. So we're going to get products minus reactants kinds of stuff going on here. If we rearrange that a little bit, I divide through by dC here, so I get dG dC. We're going to rename, this is just a name I'm giving it now. I'm going to call that delta mu. And it is an effective chemical potential for all of the products combined, right? So the chemical potential for C and D are combined together by weighting each of those chemical potentials with the appropriate stoichiometric coefficients. Same thing for the reactants over here. So this is the effective chemical potential for everything on the product side, and this is the effective chemical potential for everything on the reactant side. And so the only thing that's changed between this more complicated chemical reaction up here and our simple chemical reaction that just had one reactant and one product is that we've defined what it means to talk about the chemical potential for the whole set of products at once, not just one product, and likewise for the reactant. And so it really is still just a difference in the chemical potential for the products minus the chemical potential for the reactants, with this slight complication that we have to take all the products and weight them, all the chemical potentials, and weight them by their stoichiometric coefficients. All right. Now I won't go through the algebra, but if I now plug in mu is equal here, this mu is equal to mu 0 plus RT log of activity for A, B, C, and D into this expression up above, and do a bunch of algebra, then we get back our, again, familiar and standard expression for the change in Gibbs free energy for a chemical reaction at constant temperature and pressure. Delta G is equal to delta G0 plus RT log Q. The only differences now between the simple case and this case is that now the standard state delta G is a little bit more complicated. It's the delta G standard states from tables, from thermodynamic tables, and notice that it's products minus reactants weighted by stoichiometric coefficient. In other words, it's the same rule that we've used for now many things, right? Delta H, delta S heat capacities, and now delta G as well. We could apply it to delta A or any other quantity, in fact, if we like. And we get these values, well, we can measure them, we can get them from experiment, but in most calculations in classes like this anyway, we get them from thermodynamic tables, just like delta H's or delta S's. And then this reaction quotient is now also a little bit more complicated. It's the thing that we're familiar with from freshman chemistry, except that instead of putting concentrations in and raising those concentrations to powers, we put activities in and raise those to powers. And the fact that it's really activities that appear in the reaction quotient matters in some cases. I filled this in to make the connection with what you're already familiar with, because I know that this kind of expression is what you see in freshman chemistry, but this isn't always true. This part is not always true. It's true in most cases, many cases anyway, and in freshman chemistry, the freshman textbooks and problem sets and everything are carefully chosen so that this always works. But if you're in the real world, it doesn't always work. But this over here, the thing in terms of activity, that does always work. And so we're going to do some examples of using this formula to do calculations in a little bit here now. And I'm going to heavily emphasize the cases that are different from the freshman case, so you can see what the real true general case is, and you can see in what way this formula over here doesn't always work and what happens when it doesn't work. All right. Now, that's our general expression. We're familiar with it. I hope everybody has already remembers seeing that before and working with it in the past. I'm not going to assume that you have, but it will, of course, make things easier if you have. So let's consider one more thing before we start doing examples. This is the general expression. It applies to the chemical reaction, whether that reaction is at equilibrium or not. If this delta G is not equal to 0, then we're not at equilibrium. But we can still calculate what the driving force is. In fact, if you're not at equilibrium, then there will be a driving force. It'll be either favorable or unfavorable. The reaction will go forward or backwards. And only when you're at equilibrium will this driving force be 0. So let's consider what happens at equilibrium. If I set delta G here per mole equal to 0, then I can solve for what this, and I also set my reaction quotient equal to the equilibrium value of the reaction quotient. What that means is that all these, well, in practical terms, it means all the concentrations will be the concentrations of all the species when the reaction is at equilibrium. Right? I can plug any values of concentrations I like in here, but when I'm at equilibrium, only specific concentrations apply. And if I plug in those equilibrium values, then I get the reaction quotient at equilibrium. And now if I just solve this equation for QEQ, I get that the reaction quotient at equilibrium is equal to E to the delta G0 over RT. This thing on this side depends on concentrations, or really on activities, right? And this side doesn't. It doesn't depend on activities. It's a constant with respect to activities or concentrations. It depends on temperature, you can see. Also, in general, depends on pressure and other things. It isn't a constant with respect to every possible variable, but it is a constant with respect to activities, and so we give it a name, we call it the equilibrium constant. I think everybody has seen this relationship before too, that the equilibrium constant is equal to E to the delta G at standard state conditions divided by RT, which means that if you have thermodynamic tables, you can calculate these delta G's of reaction, and then that means you can calculate equilibrium constants, at least in most freshman chemistry classes that I'm aware of. We do those kinds of calculations pretty frequently, so I think probably everybody has done those things already also. And that means altogether that at equilibrium you get this relationship, this expression, which can be used to solve for what the equilibrium activities are, or if you like, the equilibrium concentrations or pressures or other quantities, depending on how you define activities, mole fractions and molality. There's many different ways and many different things that these activities can be related to. And we'll do some examples to see how that works. All right, this expression right here is the K equals Q expression that should be familiar from freshman chemistry. And now we've derived it. And I want to emphasize that this is only true at equilibrium, right? This Q over here has to have the equilibrium values of the activities in order for this relationship to be true. All right, one more comment. If this were a two-semester class instead of a one-semester class, we would take the time, because I think it's important and useful, to actually show what this equilibrium constant is from a microscopic point of view, from a statistical mechanical point of view. But since we don't have 2 semesters, I will just give you the final answer, and the final answer is this. The equilibrium constant isn't just a funny thing that comes out of the blue and has no meaning. It actually has a very clear and very nice interpretation, and that interpretation is this. The equilibrium constant is the number of microstates for all of the products combined when the product concentrations are at standard state, divided by the number of microstates for the reactants when their concentrations are also at standard state. In other words, the equilibrium constant is just accounting for the fact that when the reaction goes forward, you may gain or lose microstates for the entire system. If A plus B goes to C, for example, C, having only one product over here, probably has fewer microstates than A plus B had, and that means that, at least as far as the microstates of the molecules themselves are concerned, you would expect an equilibrium constant that's less than 1, right? Fewer microstates in the products compared to the number of microstates in the reactants. Now, that's not accounting for bonding energy changes, and I could go on and we could spend a lot of time talking about it, but it is a fact, and so I don't want to give people a misleading impression, and we don't really have time to talk in detail about these things. But the fact is that the equilibrium constant its role and its purpose is to account for the changes in the number of microstates that occur when the chemical reaction goes forward. All right, a few more comments about the equilibrium constant. The first thing to say is that the equilibrium constant is a unitless number. Very often in the literature and elsewhere, even in other classes, you'll see equilibrium constants treated as if they had units, and I'll talk a little bit about why that's so, but strictly speaking, and there are places where that's kind of the appropriate thing to do, or at least a useful thing to do, but strictly speaking, an equilibrium constant is a unitless quantity. You can see that in this relationship, right? This exponential over here can't have units. Nothing that's a pure exponential can have units. And that's equal to the equilibrium constant, so the equilibrium constant can't have units either. Likewise, the reaction quotient itself is a unitless quantity. You can see that in this definition over here. Every one of these activities is a unitless quantity, right? It's something like, for example, concentration of B divided by standard state concentration, which is usually 1 molar. This whole quantity is unitless That means all these activities are unitless. That means the reaction quotient is also unitless. And that has to be true, right, because at equilibrium, the equilibrium constant is equal to the reaction quotient. And that can only be true if they both have the same units, which in this case means they have no units at all. All right. Now, I said a second ago that people sometimes write and talk about equilibrium constants as if they did have units. Why is that so? And what do we do when you start seeing people talking about equilibrium constants with units? Here's why. I don't know if we'll have time to explore this subtlety and source of confusion in much detail here. We'll see. I hope we do have time because it is a source of confusion, and I'd like to clear that up for everybody before we leave this semester. But here is the short answer for the moment. Let's suppose I have this chemical reaction. I have a molecule that's maybe two proteins that are bound to each other. So AB is a complex of two proteins. Those two proteins split apart, so this is a dissociation reaction. In that case, using our rule above, the reaction quotient should be the activity for protein A times the activity for protein B divided by the activity for the complex AB. And now if I say that the activity for protein A is the concentration of A divided by the standard state concentration of 1 molar, and I do the same thing for B, and I do the same thing for the complex AB, and then I boil this down, I factor out all these 1 molar factors, I get that the reaction quotient is equal to the molar concentration of A times the molar concentration of B divided by the molar concentration of AB. In other words, it's the freshman chemistry expression that you'd expect. And if you look at that, if this has got molar concentration, that's got molar concentration, and that's got molar concentration, then this whole quantity, this first factor here, does have units. And it has units of molar, in fact, right? Molar times molar divided by molar is units of molar. But if you look at the standard state concentration factors that were actually present, they factor out, and they also have units, and the units are 1 over the units of this first factor, which means the whole thing is, in truth, unitless. But this factor with units of 1 over molar has a value, an actual numerical value of 1, which means it makes no difference from a practical point of view. If you plug the numbers in here, you'll get the right number. You'll get the right answer because this is just a 1 out in front. It's a 1 with units, but it's still just a 1 as far as calculator numbers are concerned. And that means very often people are talking, when they talk about the equilibrium, the reaction quotient here, or the equilibrium constant for that matter, they're just talking about this first factor. They talk about it as if it has units because, in fact, that little factor by itself does have units. Anyway, that's the reason. It's a matter of, well, it's a matter of conventions, and it's a matter of ignoring these standard state concentrations. In most applications, the difference between a Q with units and a Q without units doesn't make any difference, but there are lots of situations especially where the difference does matter. And again, I'll try and emphasize those kinds of situations in the examples below. All right, so that is the end of our overview of the sort of basics of the thermodynamics of chemistry, of the equilibrium properties of chemistry. Now let's do a bunch of examples. And so the first example is going to be a simple case, an A goes to B type of case, the simplest of all possible chemical reactions. And since this is a sort of biologically related P-Chem class, we'll consider a conformational change in a protein. Hexokinase, for example, undergoes a particularly huge conformational change. It's a rather famous one. So we consider a hexokinase protein that starts in an open state and goes to a closed state, and it can go back, of course, having closed, it can also reopen. And I don't know the actual value for the Gibbs free energy change for this conformational change. I'm picking a value for example purposes, not because I actually know what that value is, but so don't take this to be a given true value. Don't, put that into your research papers in the future or anything like that. I want everybody to know that that's a fake value, but it will do for our purposes. All right. So now we say, let's suppose the hexokinase concentration, the actual protein concentration for the open state here is 1 micromolar, 10 to the minus 6 molar. And the closed state has a much smaller concentration, only 1 nanomolar. Then let's calculate what the delta G, the driving force, will be when we're under these conditions. So we're not allowing things to go to equilibrium. We don't know whether we're at equilibrium or not. If we get a 0 here, then we are at equilibrium. If we get something that's not 0, then we're not at equilibrium. We're going to just do the calculation and see what we get. The delta G0 value here is 25 kilojoules per mole. Notice that it's a positive quantity. And remember from freshman chemistry that a positive delta G0, a positive standard state delta G, means that this is a disfavored reaction as written. In other words, the system doesn't really want to, at standard state conditions anyway, the system doesn't really want to be in the closed state. It favors being in the open state. And so let's see what we get. If we now plug numbers in, first of all, we want to use our formula, delta G equals delta G0 plus RT log of Q. In this case, Q is equal to the activity for hexokinase, or closed hexokinase, over the activity for open hexokinase. We choose our activity to be the usual case, the most common case, the molar concentration of closed hexokinase over a standard state concentration of 1 molar. Likewise for the open state, molar concentration of open divided by standard state molar concentration. And that means Q is equal to just the ratio of the 2 molar concentrations. We know those 2 molar concentrations. That's what we gave up here, 1 micromolar and 1 nanomolar. And the rest is just plugging into our expression for delta G, 25,000. Remember, it's kilojoules, and we're going to get joules out from this end, so you got to convert the kilojoules to joules. So 25,000 joules plus 8.314 times temperature of 300 times the logarithm of 1 nanomolar, 10 to the minus 9, over 1 micromolar, 10 to the minus 6. Notice that I gave the concentration units in micromolar up here and nanomolar up here, but our standard state concentration is in molar units, which means I have to put molar units in here. In this case, it will turn out that it wouldn't matter if I did just use a consistent set of units, but there will be cases where it really does matter, and so it's always safe to use the correct concentration units, in this case molar units, and that's what I've done here. So 1 nanomolar is 10 to the minus 9 molar, 1 micromolar is 10 to the minus 6 molar, and that's what I plugged in here. The rest is arithmetic, and you get that instead of 25,000 joules of unfavorable free energy, it's only about 8,000 unfavorable joules of free energy. So the driving force for going backwards, actually, is much smaller than the standard state driving force because we already have a very small amount of the closed form, right? We already have a huge excess of the open form. The standard state free energy favors the open form, so we've already gone a long ways towards the favorable conditions which would have a huge excess of this open form. We haven't gone quite far enough, right? Even though there's 1,000 times more open hexokinase than there is closed hexokinase, we still get an unfavorable delta G. It's a positive delta G, which means that the reaction still wants to go further. The actual true equilibrium conditions would have even less closed hexokinase than we have in this case. All right, that's one thing we can do. We can just look with this reaction, we can just look at what the driving force is for a specific set of conditions. which we chose sort of out of the blue here, but you could do it for any set of conditions. Now let's ask the question, what are the open hexokinase concentration and the closed hexokinase concentration when we are at equilibrium? Now let's use our K equals Q expression to calculate what the true equilibrium concentration will be for each of the chemical species in our reaction. When delta G equals 0, that is when we're at equilibrium, then we know that the equilibrium reaction quotient is equal to the equilibrium constant. We know the delta G0 value in this case is 25,000, so we can calculate the equilibrium constant. It's e to the minus 25,000 over 2,500. This is basically e to the minus 10, right, or very close to that. And that turns out to be 4.43 times 10 to the minus fifth, no units. Equilibrium constants are unitless. At equilibrium, I should really have written here that this is the activity of closed hexokinase over the activity of open hexokinase. In this case, that's also equal to the molar concentration at equilibrium of closed hexokinase over the molar concentration of open hexokinase at equilibrium. That's one relationship, but we have two quantities that we have to solve for, right? We need both the concentration, the open concentration and the closed concentration. That means we need another relationship. One relationship won't give us two quantities. The other relationship is this one, which says that the amount of open hexokinase plus the amount of closed hexokinase has to equal the total amount of hexokinase. And that total amount can't change, right? Even if I start converting closed to open and open to closed, I'm not changing the total amount of hexokinase in solution. We know what that total is, right? It's 1 micromolar plus 1 nanomolar, so that's 1.001 micromolar. That's the total, which can't change no matter how much I exchange between these two guys. All right, so now I have two relationships, and I can use them to solve. I'm going to call this quantity, again, sort of going back to freshman chemistry. All this whole section is really kind of a reprise of freshman chemistry, only with a good deal more rigor than we used in freshman chemistry. So I'm going to call this unknown concentration of closed hexokinase, I'm going to call it X, just to simplify the notation. And that means that if I take this ratio, it's going to be X, that's H plus, right? Or H star, sorry. And then in the denominator, I'm going to have H, but that's just the total amount minus X, using this relationship here. And now I've just got one variable that I need to solve for, that's X. And I do that, I get X is equal to K times total amount of hexokinase minus X. And then doing the algebra to solve for X gives me that X is equal to the equilibrium constant over 1 plus the equilibrium constant times the total amount of hexokinase. The equilibrium constant is 4.432 times 10 to the minus fifth. That goes up on top. It also goes here, but that 10 to the minus 5 quantity compared to 1 here is not going to make any difference, so I neglected it down here. And that just gives 4.4 times 10 to the minus 5 times 1.001 times 10 to the minus 6, which gives a final value of, for X, right, which is the same thing as our closed hexokinase, of 4.436 times 10 to the minus 11 molar. So we don't reach equilibrium in this case until the closed hexokinase is at 43 femtomolar. Way down, almost a factor of 100 down from the amount that we started with, which was 1 nanomolar. All right, so that's basically a freshman chemistry problem. I've done it in a more rigorous way than we normally do in freshman chemistry, but we'll do more examples later, and there are examples in the homework problems and so on. And everything should feel familiar from earlier classes, especially from freshman chemistry, but also from other classes, I think. All right, that's the first example. We'll do more examples in the future, but I think I'll stop there for now.